Hello, today we are going to work on merging together what we know about resolving vectors into Cartesian and polar coordinates with what we have learned about Newton's laws of motion. So let's begin by writing the formula for Newton's second law of motion. According to Sir Isaac Newton, the force applied to a vector will be to an object will be equal to the mass times the acceleration. If you don't have an overall net force, then there can be no acceleration, which is basically just a restatement of his first law, which said an object in motion will remain in motion, and an object at rest will remain at rest unless acted upon by an outside force. And acceleration is, remember, a change in velocity, so that would be a change in motion. All right, so today we have a diagram showing object A, and object A has two forces being applied to it. The first force is the 50 Newton force at an angle of 50 degrees. So we could call that 50 newtons, 50 degrees in Cartesian coordinates. Then we have a second object, which is a force of 30 newtons. And the diagram shows it at an angle of 35 degrees. However, I said that it is best for us to always describe angles with respect to the unit circle. So where that angle falls between an angle of 0 and 360 degrees. So in order to achieve that, we need to recognize that this diagram says that we are 35 degrees before the 180 mark. So it would be better to describe this angle as 145 degrees. All right, so we are supposed to determine the net force acting on object A. You may remember in a previous chapter, we had worked on doing this. So in order to do that, we must resolve both of our vectors into x and y components. Let's maybe call this teal force, force 1. So we need to find F1x and F1y. And to find F1x, we are going to take 50 newtons times the cosine of 50 degrees. To find the y component, we are going to take 50 newtons times the sine of 50 degrees. All right, so let's plug that into our calculators here. I get for the x component, we have 32.1 newtons. And for the y component, we have 38.3 newtons. Both of those are positive values, which should make sense since we're in the first quadrant. You would have both a positive x and a positive y. Now we must resolve, force number 2, our maroon force here, into its x component and into its y component. Similarly, we are going to take the 30 newtons times the cosine of 145 degrees to find the x, and 30 newtons times the sine of 145 degrees to find the y. So 30 cosine 145 gives me a negative 24.6. And that should not surprise you that we get a negative x value because we were in the second quadrant according to the diagram. Then we take 30 sine of 145 and we get 17.2 newtons. Now, the net force, you might remember, can be found by adding up the x component and the y component. So we're going to say that the net x component is going to be equal to 32.1 newtons plus negative 24.6 newtons. Just adding the two x components of the vectors together, that gives me 7.9 newtons. And then the net y component will be found by taking 38.3 newtons plus 17.2 newtons. I get 55.5 newtons. So that means that my net force can be described using the Cartesian coordinates 7.5, 55.5 newtons, which should make sense that you get both a positive x and a positive y, because if you look here, both of these vectors are in the upward direction, and the 50 newton is slightly stronger than the 30 newton. So we're going to get a resultant that's something like that, essentially. So you have a positive 7.5 for the x component and then a positive 55.5 newtons. However, they said for us to determine the net force, so instead of expressing this in x and y components, we should resolve this. Remember, to find the resultant, you take the square root of the x component squared plus the y component squared. Okay, so let's do that. 7.5 squared plus 55.5 squared, square root of that. I get a net force of 56 newtons. But because force is a vector, we should probably also find the theta, the angle that this is at. So the theta would be the inverse tangent of the y component divided by the x component. Inverse tangent, 55.5 divided by 7.5. I get 82 degrees. All right, and if we go back to our diagram, I mean, that looks pretty complementary to what I had said here or drawn in. It would be an angle of about 82 degrees. So our net force here could be described in polar form as having a magnitude of 56 newtons at an angle of 82 degrees. Now let's consider another variation of this that could be found on your homework assignment. So suppose object A has a mass of 500 grams. What is its acceleration? All right, so the new piece of information that they have now given us is that your mass is 500 grams. If we're still working with object A from this first example, we had just determined that the force being applied to that object has a magnitude of 56 newtons. We are supposed to determine the acceleration. Newton's law says that force equals mass times acceleration. So if we need to solve for acceleration, I must divide both sides by the mass. That's going to give me the variation of Newton's second law that says acceleration is equal to force divided by mass. Now, there is one issue though, because if you will remember, a Newton is defined as a kilogram meter per second squared, and they gave us a mass in grams. So we must convert from grams to kilogram. 1 kilogram is 1,000 grams, so that's going to mean 0.5 kilograms. Now we can calculate our acceleration by taking 56 newtons divided by 0.5 kilograms. I believe that's going to work out to be 112. Yep. But we are missing a unit label. Since this is acceleration, the unit label would be meters per second squared. And so our lesson today is that if there is a net force, there is also an acceleration being produced according to Newton's second law. If all of the forces should add up to be 0, there's no net force, then there can be no net acceleration. And we often refer to that scenario as being at equilibrium. Please just make sure that all mass measurements are in kilograms and that you express all angles from 0 to 360 with respect to the unit circle. And this is how you can merge resolving vectors